Well, I'd like to welcome everyone to the Infinite Games workshop. So we're starting today with Davide Leonessi. So my idea for the Infinite Games workshop was to have a series of talks that would cover some of the recent advances that have been made in Infinite Games, because there's been some really exciting developments over the past year even. And so I'm really happy to see some of the people who were behind those developments here today. And so we're going to have a series of talks all semester on various kinds of infinite games: infinite chess, infinite drafts, infinite hex. And I think in 2 weeks, I'm scheduled to give a kind of introductory talk, introduction to infinite games, and my view of the sort of emerging subject of infinite games. The aim is to look at infinitary versions of all of our favorite kinds of finite games, including chess and drafts and hex and what have you. And okay, so without further ado, let's go to Davide Leonessi, who's going to talk today on infinite drafts. Formerly, his title was a solved open game, but he has changed his title to an unsolved open game. So go ahead, Davide.
Thank you very much. Yes, so as you hinted, yes, I hope that the slides are clear for everyone and that you see my mouse. So first of all, thank you to Professor Joel Hampkins for organizing this seminar. And I'm very happy to be giving this first talk. And yeah, very often Joel Hampkins talks about infinite games as being like the frivolities of the gods. And well, I believe that those gods punish me for my hubris, my overconfidence in stating that Infinite Draughts is a solved open game. And so just 2 days ago, we received an observation about one of our assumptions about Infinite Draughts that turned out not to be true. And that will have some consequences. And I will mention this remark by Rupert McCallum that is here, that I first of all thank for being the means of the gods. And I will mention this observation in the right context.
Davide, could you maximize your screen so we get the full screen?
Can you see? Okay, now should
be
perfect. Okay. Great. So, wait, there should be, yes. Yeah, first of all, I will mention that this talk is based on the work that I did with Joel Davide Hampkins, mostly during my master's thesis at Oxford, and then in the paper that was then published in 2022. So first of all, I will make a very brief introduction to games, as we are starting this seminar in games. And so, yeah, we focus on games with 2 players and games of perfect information, which are most of the board games that we're going to consider. And so we don't have any randomness, and everything is known to players, and particularly the rules are known, the board is known at any given time. Everyone knows that everyone knows, and so on. Common conventional terminology is that a player has a winning strategy if that player can win however his opponent plays. And we start with the fundamental theorem of finite games, which was kind of the beginning of game theory in 1913, which states that every finite 2-player game of perfect information, initially with no draws, one of the players has a winning strategy. Where a finite game is a game whose game tree is finite. Where the game tree, and just to remember, is the tree that is obtained by having at each node one of the possible positions of the game, and each position, so each node has an edge to the other nodes, which represent another position that is reachable by some legal move. So really, that's kind of the structure of the game. We can kind of see what that kind of the choices of the players. So there are many proofs. Here I'll just make that I'm sure that we will see in the future. I'll give like one proof that is kind of generalizes to the infinite case. So again, we consider the game tree of some finite game, and so that this, we observe that such a tree is finite. And we start from the leaves of such a tree, and we label each of the leaves as a win for one player or the other. Here we're considering, of course, that there are no draws. Once this has been done, we go by back propagation. And so we kind of go, well, here, yeah, we think of a tree as having the initial position at the top, so the root node at the top, and then at the bottom, we have all these terminal nodes. And so, yeah, we label the nodes as a win for one player or the other. And then the key step is going from one node to the one above, to the parent of a node, because at the parent node, we will look at whose player turn it is, and we label that node depending on whether that player can move to another node, which is labeled with his own kind of color. So we can say, well, the position before, say in chess, a checkmate by white, the position before, white can move to such a position, and so we label that position by white. And so this process can be done for the whole of the game tree. And eventually the root node, which is the initial position of the game, will get one label or the other. So either one player wins or the other wins. Exactly, because then the winning player can play, so to stay, on their own level. I wanted to just make a practical example, because the first time I saw this game was during my first course on game theory, and this was in the case of chess. So the way to interpret this theorem in the context of chess is that chess is determined. Now, of course, chess allows for draws, and here chess is a finite game because there are some rules that make the tree finite. And in particular, there's the 50-move rule, so that the number of pieces on the board has to strictly decrease, at least like by one every 50 moves. Otherwise, like the play ends and it's a draw. And so in standard chess, either white has a winning strategy, or black, or both of them have a strategy to force a draw. Comment on pawn moves? What do you mean? Sorry, Matthew.
The 50-move rule is that either a capture or a pawn movement, but only finitely many of those can happen.
Okay, thank you. Right, so mostly taking this just because I wanted to take a picture from my first textbook on game theory. They also owed this proof to John von Neumann, but I'm not sure if von Neumann was aware of the proof by Zermelo. Anyway, that's kind of somewhere in between there, between 1913 and early 1950s.
Zermelo specifically talked about chess. That was his main purpose in that paper, was to handle the case of chess.
Yes. Also, right, and hopefully we will get an English translation of it at some point of Zermelo. I don't know if at some point I talked about it with Clara, because I'm not sure if there is an English translation of the Zermelo paper. Yeah, anyway. So yeah, the point is, here is we just have a graphical description of the finite tree of the game tree of chess. And so again, we kind of start from the bottom and kind of label each node by who can win from that specific position. Right, so this was the finite case. Now we can move on to infinite games, which are the main topic of our seminar. And so I would define a game to be infinite in the case that its game tree is infinite. And in particular, we focus on games whose game tree is infinite because players can be allowed to choose among infinitely many moves in a turn. That's going to be our main focus, at least in this talk. In particular, we focus on games which are open. So a game is defined to be open for some player if that player can only win infinitely many moves. And so that really, and so that in the space of plays, a certain play, so which is kind of a branch in the game tree, is in the winning set of a certain player, only if that branch is basically kind of determined by just a finite subpath of it. And this is the same as saying that the whole of, so the collection of all the winning plays for a certain player is open within the game tree with the product topology. So yeah, the collection of the winning plays really is the winning condition for that player. So here I can say the theorem of open determinacy of infinite games by Gale and Stewart, so that in any infinite two-player open game of perfect information, one of the players has a winning strategy. And in the same way, if we also allow draws, then there's also the third case of both players having drawing strategies. And yeah, this can be proved basically in an analogous way to the Zermelo's finite theorem, because, well, plays are fundamentally finite. So at least, like, if we just focus on just on the winning strategies, so we first look at whether in a game the first player has a winning strategy. So the way to prove it is like we focus on whether the first player has a winning strategy, and so we look at all the plays which are winning for that player, and all of those ones are finite. So we can look whether the initial position has a winning strategy for that player, and then we can do the same for the second player. And yeah, if there are draws, we just need to be a bit more careful, because then we just have to figure out, like, if neither player has a winning strategy, and then we get that both can force a draw. Anyway, we will see a proof of this in also with game values. And so the reason for which we focus on open games is that they are the class of games that allow us to develop the theory of game values, which generalize the typical situations in chess that are called mating 2, mating 3, which are positions for which a position is said to be mating 2 for a certain player, say white, if white, that player, can win by playing for at most 2 moves, however the opponent black replies. So the idea is that mating 2, that number gives an idea of the distance from victory, and the game value is an ordinal that measures this number of moves for the open player to achieve a win. So the open player is the player that we're kind of giving the value for in the position. And we will start with some examples. Also, because my talk is not just about infinite games, but it's specifically about drafts. So I start talking about finite drafts. I assume that everyone is familiar with that. Takes place on the standard draft board, 8 times 8, and the moves are all diagonal, and there are captures that happen diagonally. Now we're gonna look at specific examples. The main thing that please take from this picture is that black pieces will take the convention that go upwards, and red pieces will go downwards. We call pawns the simple pieces that only go in one direction, and we call kings the special pieces that actually go in all 4 directions. So both upwards and downwards in all the diagonal.
If I could interject, because I'm not sure if there are any other Americans here, but this is the game, of course, known as checkers in the United States. So checkers, drafts and checkers, same thing.
Yeah, indeed. Yeah, I think that officially, like, drafts is placed on the 8 times 8 and checkers on the 10 times 10. But yes, then they're all interchangeably. Or like there's international checkers, and there are some variations on the rules and on the actual draft board. But yes, drafts or checkers. Especially now that I'm in New York, yeah, I should probably say checkers. But yeah, anyway, we started this work in the UK, so the English terminology sticked. So yeah. This is the finite draft board, and of course we don't want to limit ourselves to this finite board, but we want to consider the infinite edgeless planar board. So we think of playing on the integer lattice, and again, the game then is kind of, we think of the most natural generalization of the game, so that in this infinite draft board, the game kind of locally happens in the same way, so always on the dark squares and moving diagonally. So in this case, we can see, like, so this will be a king with these kind of double circles, and this king can move, like, for instance, it can capture this first red piece and go on to A, or it can capture all the way A, B, C, D, E, and then it would have to stop, and then would be captured by a red pawn that, remember, go downwards onto F. And yeah, now I will specifically say what the rules are. So first of all, we'll have the forced jump rule. So now we will start by assuming all these rules that I'm going to talk about, and then we're going to talk about subsets of these rules in following constructions. So for now, we're assuming a forced jump rule, which means that if a player is faced by a capturing opportunity, so capturing or jumping opportunity is the same, then that player has to go through with the capture, that is the jump. So in particular, in this position on the right, if black is to move, then black cannot just walk away from these opportunities of capturing, and so it cannot go back down to E or F. But for instance, it could jump to D. That would be a legal move. Now, except for the other one, we want to consider also the forced iterated jump rule, which means that once a jump is made, so once a jump is kind of initiated, the player has to make a so-called maximal jump. So in particular here, black cannot just jump to A because it would find itself in kind of a local configuration in which it would still be able to make another jump. So a maximal jump would be to A and B, and so kind of ending in B, or to A and C and ending in C. Of course, like black has still choice of how to behave, so it can still jump just to D. So that's kind of part of the freedom of the player. But yeah, also the jump to D is indeed a maximal jump. And the winning condition is that, in the same way as in Infinite Draughts, is that the first player who has no legal move loses. And that usually can happen either by not having any piece on the board, and so of course there are no legal moves for that player, or if there are still pieces on the board, then all those pieces are somehow kind of stuck and kind of boxed in some other pieces, and so they cannot really move. Also, I mentioned open games, and of course, we only focus on open games of Infinite Draughts. So in the sense of games that start from initial positions that allow only for open, for players to win only infinitely many moves. And we do this by deciding, like I mentioned, that plays that last for infinitely many moves are draws, which is also kind of a natural generalization of the finite case, as we mentioned before, the 50 move rule or the pawn rule in chess, and also in drafts there's like 40 or 50 move rule, which really are kind of this proxy for stopping players from playing for infinitely many moves, because those are draws. There's one extra rule that I'm going to mention, which is the infinite jump rule, which is specific of Infinite Draughts. So in Infinite Draughts, like a position like this one can happen, where a black piece, for instance, is faced with this infinite ladder of alternating red pieces, so that black can make well, especially like with the forced iterated jump, the question is, what is the maximal jump? Well, a maximal jump here would be like capturing all the infinitely many pieces that go onto this diagonal. Well, in that case, we agree that after that one single move, because it's kind of an iterated jump is a single move that goes up to diagonal. After the move, all the red pieces would disappear from the board, so they would all be captured. And the point is where the black piece is after that move. And the thing is that that black piece is nowhere on the board, because its position is not assigned to any of the squares on the draft board. And so it somehow vanishes and kind of goes off the board. It somehow goes off, it kind of goes off the edge in this edgeless board. And so in this case, it's a form of self-capture, because it's kind of capturing itself, the black piece. In this particular position, after black captures all the red pieces, it would be red's turn, and red would have no pieces on the board, so red would lose. But if red had another piece, like randomly somewhere on the board, red would be able to move that piece, and then it would be black's turn, and black would have no pieces on his own, and so black would lose. Just to remind the winning condition. Right, so the black piece disappears from the board. So now we look at some examples of game values. So we start with finite game values. So this position, where red is to move, has game value 2. And it is game value 2 because it really is a mating 2 position for red. Because, well, red is to move, so red moves this red pawn down to A, which is kind of a bait. And so at that point, because of the forced jump rule, black has to jump over this kind of bait, and then it's stuck in front of these 2 red pieces, and so red can jump a second time and capture the black piece. So the game value is 2 because red makes 2 moves, and so we only count the winning player's moves. This position can be iterated, and so we can construct a position which uses the same idea to construct a position of game value 3. So also here again, we have that red it's red's turn to move, so red goes down to A, which is the first bait, and then black has to jump over, and then red uses a second bait to move it down to B, and then black is forced to jump over this second bait, and then it is captured by red for a total of 3 moves by red. Now, this position, of course, can be iterated for any finite number. So for any n, we can construct that position like this, a finite position with game value n. And now we kind of collate all these positions into constructing one position of game value omega, in which we have this blue kind of infinite ladder, as we had seen for the infinite iterated jump rule. And from this kind of main ladder, we have all these kind of branches that are kind of offshoots of this ladder, which are placed, by the way, at increasing distances, so that we are sure that there can be no interaction between different branches, so that play will happen as I'm about to discuss. So here, by the way, black is, so here consider black be a king, that and it is black's turn to move, and the game value is defined for red. So black, of course, here we have the forced jump rule, so black has to kind of get over this big tree that is facing, so it is at the root of this kind of tree. And as discussed for the infinite iterated jump, black cannot just go off this, I mean, it can go off this infinite ladder, blue ladder, but the point is that it would just capture itself, and so it would lead to an immediate loss. But of course, so black aims to kind of delay loss as long as possible, if that's kind of the best outcome, because black will not be able to escape from this structure and will not be able to kind of wander off in the wilderness of the empty board. So the point is that since it has to get on the ladder, and it doesn't want to stay on the ladder so that it doesn't lose immediately, it will have to go onto one of these branches, and so it will get to rest on some of these squares with some finite numbers. And here we are thinking of having for each finite number one of these finite branches in the same way as they were constructed before. And once black reaches one of these finite numbered squares, then it will lose after that many moves because of the way that these positions were constructed. And the interesting thing is that playing like this really is like counting down from omega, where the first kind of step in counting down is this commitment by black of choosing one of these offshoots. And so black could count down from omega by starting from 4, for instance, and then would count down to 3, 2, 1, 0. And when it reaches 0, of course, red would win. And the point is that red can definitely win however black plays. And these are the, and yeah, of course, black only makes this commitment at the very beginning. And this really is these are the features of positional game value omega. And so now we can define what game value is. So if we think of a game which is open for both players, which we call red and black in this case, and the game value of position is defined recursively. And this should remind us of the proof I mentioned of the of open determinacy and also Zermelo in some way. So first of all, we look at the positions which are already won by red, and so now we define the game values only for red. So consider the positions which are won by red, and so if the game kind of at a certain position, okay, here we're kind of looking at a specific position, then the value of that position is 0. Then we look at the positions which are not yet won, and if from those positions red can move, and it is red's turn, and red can move to a position which has some value, alpha, then red will look for the smallest value among all the positions that it can reach, and it will kind of decide to move to that one because the one with the smallest value is the one which is nearest to winning. And in doing so, it will make one move. And that's why the value of the position that it starts from will be just alpha plus 1, because then it would make one move and it would reach position of value alpha. And then if it is set like black's turn, so the value of the position, so if black can only reach positions of with some game value, then black will aim to reach the position with the highest game value, so that it is kind of as far as possible from losing, because it's from the black's point of view. And that's why in that case we look for black would aim, yeah, so the position from which black plays will take as value the supreme of all those values. If instead there is one position that is reachable, which has no game value defined, then also that initial position that black is moving from will have no value. And now we can just observe that. So once we define all these game values for all positions, we can see that from a position which has some successor game value, of course, like I am assuming the knowledge of ordinals because no one really asked me how to find the password of the seminar. So that was a great way to ensure that I can assume this knowledge. So again, yeah, if we're given a position where which has value alpha plus 1 for red, then it means that if it is red's turn, then red can move to a position of value alpha, because that's exactly what it means for a position to value alpha plus 1. Well, instead, if it is black's turn, then black simply cannot reach a position with higher value or with no value, and that's which would be the aim of black. And that's exactly because that game has that position as a value, because if that was possible, then the position itself would not have a value. And then instead, in the case that a position has a limit game value, limit ordinal as a game value for red, say, then black can only play to reach position of lower game value. So in the same way that we saw for a position with game value omega. Exactly because the limit ordinals can only arise in positions where the losing player is playing by definition. And yeah, I see a question by Ariaman.
Hi. In the definition, why do we use the supremum and not the maximum?
Right, because, well, if you think about the position in value omega, here, well, there's no maximum, right? I'm putting all the finite values, so black can reach any finite value. And so usually we say maximum when the maximum is reached. So if here it was only 1, 2, 3, and 4, then the maximum is 4. But since I'm putting all the finite natural numbers, then I have to take the supremum.
Okay,
so,
thanks.
Yeah, okay, yeah, welcome. Okay, so oh, and then final observation: if a position has no value for red, then simply red cannot reach a position with value, because otherwise, because that's the meaning of not having a value. Because otherwise that position would have had a value. Instead, black from a position which has no value for red can reach another position which has no value for red. So these two ways of kind of behaving, this kind of ways of making moves by red and black, we can identify them and give them names, because the goal of red is to decrease the game value so that it can eventually reach a position of game value 0 and win. And the strategy that red has to follow is the so-called value decreasing strategy, so that when red starts from a position with a game value, then it can win, and it can win finitely many moves. Otherwise, if a position has no value for red, then red cannot do much and cannot follow the value decreasing strategy. On the other hand, black can make sure that the play only goes through positions that have no value for red. And so that's the value avoiding strategy for black. And the thing is that in an open game, which means a game which is open for both players, then either the initial position has a game value for red, say, or it has a game value for black. It cannot have a game value for both, because that would mean that both can use the value decreasing strategy and both win, but that does not make sense if the winning condition is well defined, which we assume it is. Or neither player, or the initial position has no value for either player. But in that case, both players can use the value avoiding strategy, and so they would reach a draw. And so this is just a proof of the fundamental theorem that I mentioned at the beginning about open determinacy. Yeah, so these are kind of strategies that we will see in action very soon. Now we reach the main theorem of our paper, that is that every countable ordinal arises as the game value of a position in infinite draughts. And here we follow the initial idea that was used in chess in the three-dimensional case. And this is a proof idea that we will see multiple times, I think, in this seminar. So the idea is to embed well-founded trees in the board, and so well-founded trees which do not have infinite branches, and kind of embed them into some positions. And then once we kind of embed these trees, we want to make sure that the play proceeds as though, well, in this case, black is climbing this tree, and eventually black loses when reaching a leaf. So we think of black trying to find the longest branch possible, but since the tree is well founded, then there would be no infinite branch. So black would eventually reach a leaf and lose. And in this way, we'll make sure that the position has a value for red, and that red wins infinitely many moves. So in this way, the game value will track the ordinal rank of the tree, because if black makes every time one single step to kind of climb this tree, then it will eventually lose when reaching. So this will be basically, they will be defined in the same way: the rank of the of this tree and the game value of the position. So in a way, there's some kind of analogy between the game tree of the game that we produce and the tree that we're kind of embedding into the game. They would be kind of highly correlated. So we need one small lemma for doing this, to make sure that we can embed any kind of tree we want into the draft board. And the fact is that we can embed the full binary tree in the infinite draft board, where for a tree here, we're kind of thinking of, I had originally called this a king tree. So think of this tree where, like, we have this black king at the bottom, and then we got this full binary tree over it. And basically, well, it's not too difficult to see that such a binary tree can be constructed, because one can start kind of allowing it to branch, and then and kind of keep it branching and kind of going upwards. And then when there's not enough space for it to keep branching, we can just let the leftmost and the rightmost branches to kind of keep growing sideways, so that there's more space in between, and then let them branch again. Or otherwise, it can be done by induction and kind of constructively constructed. So yeah, this is something that will pop up again later. And so we start by considering the we do this now with 4 different sets of rules. So now we start with the forced jump rule. So players are forced to jump when they can, but we don't assume the forced iterated jump rule. So we'll prove this by induction on the game value. So we're already seeing game values of finite game values and the position of value omega. So think of having constructed infinitely many position with game values alpha 1, alpha 2, alpha 3, and put them in increasing order. That's very important. Well, non-decreasing order. And think that they've all been realized as well-founded trees in the previous way. And that they can be embedded in the board. Then we're going to construct a position that looks like this. So in this position, it is black's turn to move. And I claim that this position has game value that is the supremum of the successors of all these game values which have already been constructed. So here we see that the black king can kind of, so this blue ladder really is kind of the infinite blue ladder that we're seeing also in the position of game value omega. So black could go all the way down this blue ladder because it's just kind of alternating red pieces, but it's not going to do it because it would lose immediately. So black can rest in these numbered squares because even though there are these many red kings, these red pieces are actually pawns, so they only go downwards. So black can reach 1, and then at that point it can rest there because red cannot immediately capture black. Of course, like black then is kind of somehow glued to this tree because of the forced jump rule. So black, when it reaches that square, then it keeps having jump. It does have to keep jumping, and red can move at most one of them, one of these red pieces in the reply move, and so black will still have to either kind of keep going on the ladder or going down one of the branches. So yeah, so the point is that black with his, so the standard play here is that black will stop on one of these number squares. Red will kind of break the symmetry of the blue ladder, and then black will be forced to go down the branch that it is currently at. Also because in the meanwhile, it will have captured all the pieces behind it. So, and once it kind of goes down this branch, say alpha 3, then it will be basically at the root of a tree that we have already constructed, which has game value alpha 3. And well, the nice thing of drafts is that we can kind of bend all these trees as we want, so to make sure that they really fit into the draft board. And this whole construction will be just like a subtree of the full binary tree. So we are sure that this can be built because of the lemma before. I think this pretty much covers it. Well, I mean, it's important that the game values are kind of ordered in this way, in non-decreasing order, so that if black reaches square 2 and red decides to kind of break the symmetry in this alpha 2 branch, then black can just keep going down, and it can still kind of reach position with like kind of a higher game value. Yeah, this is exactly the features as like that black with the initial position commits to a specific game value, because then the best move for red would be to break the symmetry on the blue ladder. So yeah, this position does realize a game value like this, supremum of alpha n plus 1.
Yes. Can I suggest maybe you explain why can't red just continually harass black by preventing him from entering the subtrees? So what would, I mean, red could certainly play in that way, but why is that a bad idea for red?
Well, if red so basically kind of keeps bringing the symmetry of each of the trees, then black would make infinitely many moves down the blue ladder, and so yeah, the play would go on for infinitely many moves, and so there would be a draw. Yes, thanks. There would be a draw by the because yeah, plays that go on for infinitely many moves are draws. So yeah, eventually red is forced to, well, I mean, it is in the interest of red to eventually break kind of the blue ladder and force black to go down one of these well-founded branches. Yes.
And what prevents black from just directly entering one of the subtrees on the first move without stopping to rest?
Because yeah, that would also be a possibility for black, definitely, to go straight down. But it is in the interest of black of kind of choosing a game value as high as possible, so to kind of remain as far as possible from winning, and so it would just be kind of wasting a move. So if black, reaches square alpha 1, square 1, then it's at the bottom. It puts itself in a position of game value at least alpha 1. But if it goes down the branch, then it will be some. Well, if alpha 1 is a successor, then it will have it will reach maybe a position of value alpha 1 -1 or -2, or maybe even lower if alpha 1 is a limit. So yeah, that's also why black will try to go as slowly as possible, kind of on the side, and black, whenever possible, will try to go down the blue ladder, because the farther down the blue ladder black goes, then the higher up the values are. And that's exactly why the values are ordered in non-decreasing order. Yes, I think this covers pretty much all the possible situations that can arise in this position. Unless there are questions, I see some questions in the chat. This must be very clear, because that's kind of the theoretical background is here. So there are any questions to ask for the game to be open for both red and black and not just red? Oh, Matthew, yes. Yeah, that just simplifies the situation if the game is open for both players at the same time. Otherwise, I'm not sure what was the slide that you were looking at. But otherwise, yeah, I mean, it's important that if the game is open for only one player, then you can only define game values for that player. And there are games like this, like the famous Conway's Devil and Angel game is open for one player and not open for the other one, because one player wins when the game goes on for infinitely many moves. Oh, right. Sorry, that was answered. Yeah. Non-iterated jumps still enforced. Does black have to capture at all? Oh, right. Okay. Yes. Definition game values. Okay. I think this answers all questions. Okay. So if this is clear, now we can kind of consider different sets of rules. And so the background, the proof will remain the same, but we're just going to change the implementation of these nodes. So in some sense here, yeah, we're kind of constructing all these trees in this way, but we're just going to construct them differently, but then the proof will be the same. So the first case, yes, is a construction with, yeah, so here we are dropping the forced jump and we are introducing the forced iterated jump. So here it's kind of just a simple modification, because we only need to kind of encourage black to actually get onto the blue ladder and stay onto it. So we're adding these so-called guardians, these red kings that are enough to kind of make sure that black gets onto the ladder, because if black just tries to walk off in any direction, then it is immediately captured by, yeah.
Have you said it correctly in the slide title? I think you don't want either rule in this case, right? I mean,
oh, right. No, it is without
the forced iterated jump and
yes.
without the forced jump. Neither of them is what you want, right?
Yes, because if there was forced iterated jump, then well, then black would just keep going all the way and it would immediately reach a leaf. Yes. Sorry. Yeah. Thanks for pointing that out. So yeah, before we did not have any. Also, I may notice that also here it was very important that there was no forced iterated jump, because otherwise also here black would go all the way down and would immediately reach one of the leaves here. So yeah, it's very important that here is no forced iterated jump, no forced jump. So here, again, we're just like encouraging black to stay on track. And again, when it reaches one of these resting places that work in the same way as before, it cannot just walk off by going kind of upwards, because there are these red guardians that make sure that it would be captured immediately. Yeah, here any other observation? Well, I think that here then it's the same in the sense that red, it's in the interest of red of breaking down the symmetry on the blue ladder. And so eventually red will force black to kind of go down one of these branches. And yeah, black also will try to go kind of as fast as possible down the ladder and as low as possible on the kind of colored branches. So in that sense, it works in the same way. Now, the problem is that if here we do add, yeah, so we've pointed it out, what's the issue with adding forced iterated jump? So for forced iterated jump, we really want some position that allows black to stop, without having any opportunity to jump, and then make an extra move to reach another position from which to restart again, kind of descending the tree. And that's why we need slightly more complicated position, which still is much simpler than the very original one in my dissertation, because then I did need to contact my the world champion of Infinite Draughts that was kind enough to review it because it was particularly convoluted. This one, I think we can be a bit more sure about it without having supernatural power, without having extensive knowledge of the game. So yeah, so here we are assuming both rules: force rate jump and force jump. So here you have the blue ladder that goes there, and here this is kind of the first node of the from which like black can just branch off. And the idea is that now the resting place will be A. So black will go down. By the way, here, of course, we need no guardians because we have force jump. And so black, and also we only need pawns, by the way, on the ladders because black will have to go all the way down. It doesn't need like the king that is kind of, so you saw before we had all these kings that made sure that black did not stop in a non-resting place. So really here, black, the only resting place is A, which say that it chooses this node and stops in here. Then there will be one reply by red. Well, also one thing about this position is that if before we had only one copy, so in the, sorry, I will have to go back 1 second. Here we had that we assumed the presence of trees that realized these game values, alpha 1, alpha 2, alpha 3. And so from one node, it could reach one tree. It was at the root of exactly one tree with game value alpha 1. That was a position of game value alpha 1. Here we have that instead, like all of these colored branches represent trees which have a given game value. So instead of having just one copy, we'll have 4 copies. And now it should be clear why soon. Because the point is that black reaches A, and then red has one opportunity to kind of break the symmetry in somewhere. So it can break the symmetry in, say, on either the left half, so on either of the purple branches or of the green branches, or maybe somewhere else completely different on the plane. And the standard play will be that, say, that red breaks the symmetry on one of the purple branches, and then black from A will decide to go on to 2, which is at the root of these 2 trees on the green branches. Then it will be again red's reply, and red will break the symmetry of one of these green trees. And then black will still be at the root of exactly one tree, which is pristine, kind of exactly as it was designed at the beginning. And so it will have the intended game value. And so black would be able to start climbing it. And so that's kind of standard play. Then a few things go differently. So in particular, there is this so this structure above is put there so that black cannot decide to, so once black reaches A, it cannot just decide to wander off again on either of these 2 gray squares, because then red would be able to kind of move down this yellow pawn and kind of, that would be a bait for black again, so that black would have to capture it, and then it would be very quickly captured. I think, yeah, if black goes here, then red can move it here, and then black has to go up here and then gets captured. And if black goes here, then again, red goes here, and then black has to go up, and then it's captured. So that's because of the force jump. Other things that could go differently is if, well, black has to go down, so red could make some different, red cannot force black to make a force jump, so red cannot immediately give, as a reply to the initial move by black, an extra force jump. So if black is here, then all these pieces can only go downwards, and so yeah, red cannot force black to do anything different. Yeah, so any questions about this position? Okay, so I think that, because I don't see the top of my presentation, but so yeah, so here we have a simple consequence of this, which is that so we usually define as the omega-1 of a given game, of a given infinite game, as the supremum of the values which are realizable in it. Now, we did not state it as a corollary in our paper, but it's kind of an immediate consequence of the theorem that we've just proved, which is solid, and we are happy with it. So what we've just shown is that the omega-1 of infinite draughts is at least true omega-1, in the sense that, well, all the countable ordinals can be realized, and so the supremum of all of them is at least, well, it is omega-1, and so the supremum of all the values realizable in infinite draughts is at least omega-1. Now, we kind of initially stated it as an equality because, in fact, like the notation kind of gives an idea of it, is that in most games, which are natural generalizations of natural board games, we have that the boards are usually countable in size, and so each player only has countably many moves available at any given time, any given possible turn, and so it looked like it in drafts as well. And if at any turn you have only infinitely countably many moves available, then it means that the possible game value of that position will be at most a countable supremum of other game values. And so by recursion, but by induction, it means that only countable game values can arise in such a game. But that's not the case in infinite draughts, as Rupert McCallum pointed out 2 days ago. So here I will just repeat the remark, that is that there are positional infinite draughts in which one player can choose among more than countably many moves, but uncountably many indeed. And the fun thing is that I've already shown you a position from which that happens. And that position is the full binary tree, because which indeed is from our original paper. So the Black King here is at the root of this full binary tree. And the point is that there are countably many positions in which Black can put itself in, but there are also uncountably many ways in which Black can disappear. So Black can just, well, especially with the forced iterated jump rule, Black would have to just go down one of these full infinite branches of the full binary tree, and yeah, indeed disappear. And in any way that the Black does it, it reaches a different position. So those moves really are distinct. And so this opens the question about whether there is a position of infinite draughts that maybe has uncountable game value. So I think that we are all very skeptical about that possibility, but it's not so obvious to disprove that. At least we didn't figure out in 2 days. So this is some open question that makes this game very much unsolved at the moment. Yeah, because we want to rule out the possibility that the omega-1 of draughts is strictly greater than omega-1, which would also imply that we have to give a different name to the omega-1 of an infinite game, obviously. And yeah, so maybe we can talk about this more during the question time. And I think that I'm getting towards the end of my hour, so we'll just go very quickly through the last 2 slides, which are that, so first of all, like that we implemented all this strategy, the way that we did was to construct trees and to embed them in the board. And there's a nice consequence of this is that if we want to reach position, so if we want to have a position of game value alpha, then we have a way to put a tree of rank alpha into the board. But this can be done in many different ways, because there are many trees that have the same rank. And so in that sense, we can look at different ways in which the losing player can climb such trees. And so yeah, here I just give the 2 examples of trees of rank omega. And so these kind of give rise through our method of constructing positions to distinct positions. And so Black, well, in some way, of course, this is kind of a subtree of the other, but we could think of trees which are not the subtree of the other. And so that just makes it a bit more, the game is kind of this full expressive power that is kind of nice. And I guess desirable, and that's just a consequence of our very constructive method. Then one last observation about computable play is that also this kind of follows from our very constructive method, which is that there is a computable position in infinite draughts such that red has a computable strategy to win against any computable strategy. And also red can force a draw or better against any also non-computable black strategy. On the other hand, black has a non-computable drawing strategy. Now, this is also comes from proof technique from the chess paper of Hills and Hampkins in 2014, which rests on this fundamental fact that there is an infinite computable binary tree which has no computable infinite branch. And once we have this tree, we can embed it into the draft board in the same way that I have shown. And once we embed it into the draft board, we can make sure that black is climbing, like the play for black really is climbing for this tree, with this computable tree with a non-computable infinite branch. And so since T does have an infinite branch, which is non-computable, black will have a non-computable strategy to climb it, to climb that specific branch, so that it doesn't get stuck into a terminal node where black would lose. And so if it goes up this infinite branch, then the play would be a draw by infinite play. And yeah, the point is that this strategy is not computable. And if instead black plays according to a computable strategy, then maybe it will follow this infinite branch for a while, but it will have to get off it at some point eventually. And so black will find himself stuck at some leaf and so lose. And in either case, yeah, red just has to make sure that black keeps climbing the tree as we had seen. And yeah, this is just kind of a different way to, well, another specific case in which we can apply this constructive method. And yeah, that's all for me. So thank you very much for the attention.
Thank you very much.
Thank you.
Thank you.
So are there any questions?
I would have a question.
Go
I know
ahead.
it just came just now to me when you said your last theorem, and you said there is a non-computable drawing strategy. Can we make that any preciser, like where on the arithmetic hierarchy or hyperarithmetic even the complexity of that strategy can lie?
Oh, I'm not sure.
You can make it low, of low Turing degree, which means so a real or an infinite set is low if its jump is equal to zero jump. So in particular, it would be strictly less than the halting problem. So very low in the arithmetic hierarchy, because every computable binary infinite tree has a low branch. That's the low basis theorem. And so therefore there will be a strategy for black of low complexity.
Okay. You said so lower than the halting problem even?
Yeah, strictly lower than the halting problem. Yep.
Okay.
But not computable. So intermediate between computable and the halting problem.
Oh, interesting. I mean, then that's kind of like a very natural way to get like something that is strictly between computable and halting problem.
Yes, yeah, exactly.
It's natural. Interesting. Okay, thanks.
I think that might be if you could have a position where on the first move, red chooses between infinitely many options, and then black chooses between infinitely many options, and then red chooses between infinitely many options, etc. I think you could push into the higher into the arithmetic or hyperarithmetic in that way. In particular, I think I can imagine some sort of
But you want a computable infinite branching tree, game tree?
Yes.
Yes. Whose branches are all of high complexity. Is there such a thing? Let's see.
So something which I'm imagining is, say I have a statement in Pinot arithmetic, and it's got a there exists for all, a bunch of quantifiers out front.
Right. Yeah.
And then for red to win, red somehow needs to make this statement true. And for black to draw, black needs to falsify the statement. And then so if you can have infinitely many choices, you can have a win condition at all choices which make that statement true. And then that should be computable.
Yeah,
so
I think so, yeah. So basically you're just writing down the tree of what it would be like to certify the truth of say a sigma n statement in n steps, right? You're going to end up, is it really true for the exists player to win that game? To have a winning strategy in that game would tell you the existential witnesses for any possible universal candidate put up by the universal player, right? Is that what you mean? Or?
Yeah. And so in particular, you'd get a computable position where the result of the position what am I saying? You'd get some sort of completeness statement among all.
Right.
In fact, I think even hyper-arithmetic statements.
I think it would push into hyper-arithmetic.
Yeah. And so this is something which I'm going to try and do in chess, because my original chess position only let black choose between infinitely many options, but it's not hard to mirror the setup for white and then do something like this. And
Right, very good.
But yeah, I'd be curious if that's possible in drafts, because I was thinking a bit about it and I couldn't.
It might be easier because drafts is way easier than chess, actually.
Yeah, no kidding.
All right, any other questions?
Yeah, one more.
Chess does not allow for uncountably many moves. Any position. That's the only thing.
That's true.
Yeah. No, that's very interesting. Yeah, actually, I was going to suggest something, which is that a lot of variants of drafts that I've seen, like I think Russian checkers, it might be called, they have this flying king rule. I don't know if you've seen it, but the king is much more powerful and can jump from like a bigger distance, and sometimes it can even jump pieces in a row.
Right.
And I was wondering if, with the addition of the flying king rule, if the uncountable game value might be easier to find.
So does the king move like a bishop, like in chess? Or
but only when it's jumping tends to be the.
It can jump over huge collections of pieces, not necessarily connected.
Yeah, there's a number of different regional variants of drafts which have something like this.
Right.
And one of the particular annoyances that we see in chess is that it's sort of very hard to get something very global. All the chess constructions really rely on these long range pieces. It would be extremely interesting to get anything in chess that has short range pieces.
No, but if it's impossible to get infinite game values that way, I mean, with short range pieces, then you're taking the supreme case of a finite set, so you'll never get value.
Right. The result for short range pieces that I don't know either way is computability of if white can win, right? Because you show that the mate and end problem is decidable, but I don't necessarily see why. Yeah. Okay. I'll need to review that, but maybe Andres knows more about that than I would. But
all right. Anyone else have remarks?
I've got one. Yeah.
Sure. Go ahead.
So thank you once again, Davide, for the talk. I noticed that all of the Omega-1 positions we looked at have an infinite number of pieces. And as we know, it's possible to construct Omega-1 positions in chess which have finite pieces. In fact, you can just have like two offending pieces and one defending piece. So like 3 overall plus the kick. Is it possible to construct anything in Infinite Draughts, checkers, with finite pieces?
So thank you very much for the question. I believe you mean value omega, right? Like
yeah.
So yeah, that's a very good point. Well, let me think. I mean, it doesn't seem like I could rule it out immediately. Like I feel like in a way, like the problem is that pieces can, if there are finitely many, they can probably kind of wander off more easily. So certainly probably the forced jump rule would be necessary to make sure that they kind of all stick together and kind of jump as needed. But then if they keep jumping, then they're reducing strictly the number of pieces on the board. So maybe eventually the game value doesn't seem.
It can't happen because it's impossible for
Oh.
the reason that I mentioned to Matthew, namely, if the game tree is only finitely branching at every move, which it would be if there's only finitely many pieces in drafts, then you're never going to take an infinite supremum, and so the game values will all be finite.
But red also wins if black has no legal moves, right? Is it possible to construct something
the
like
difference with chess, I mean, because you mentioned there are finite positions with infinite game value in chess, but they all have bishops, rooks, or queens, because those pieces make the game tree infinitely branching, and they're required because of the reason that I just gave. If you only ever have finitely many moves available, then you're never going to have an infinite game value for such a game.
I have a proposal. What if you have like a circle of red pieces around your singular black piece? Is it possible to like have, I don't know, a space in which the black piece can move for omega turns, but the circle gets smaller over time?
It's not the question of whether the tree itself is infinite. It's the question of whether every node in the tree is finitely branching. If there's only finitely many black pieces, then there's only each piece has at most 4 moves available. Or if there's iterated jumping, there's some finite number of moves. Because if there's only finitely many red pieces also, then the total length of the iterated jumps is also bounded uniformly. And so therefore the game tree will be finitely branching. And that's what causes all the game values to be finite.
What if we use the Russian version where our black piece is now like bishop-like? Is it maybe possible?
Yeah, that's possible. Yeah, maybe. No, well, still, even if it's, I think even with the rule that Matthew had mentioned, I think if there's only finitely many red pieces, then still you can jump very far, but still only finitely much. With such, it's not like you can move like a bishop, a billion miles away if there aren't pieces that you're jumping over. I think the usual flying kings they're able to jump long distances, but they have to jump over something and then they land immediately after, if I'm understanding how they work correctly. But you're right, if there was more like a bishop kind of piece that could move infinitely far, then it's conceivable. I mean, so one could invent a kind of fairy piece like that. And for such a kind of version of drafts, then it's conceivable one could get infinite game values.
I think you're right, though, because, I mean, since we do need to go over a piece to get to position XY that's infinitely far away, this doesn't work with finite enemy pieces anymore.
Yeah.
But, I don't know, someone would have to prove it properly, I guess.
Well, yeah, anyway, that's, that's pretty much an answer, so, yeah.
I was thinking about Rupert's remark about the uncountable branching game tree in drafts. And what I realized is that if you have a position with only finitely many black pieces, and for example, all our positions to get the high game values all have only one black piece, just the one black king, that's it. Then we get the result, because even though there's uncountably many possible moves for that one black piece, black doesn't want to do any infinite iterated jump, because then he would disappear. And so therefore none of those moves are going to be any good for achieving game value, because they're all going to lead to a loss relatively quickly. And therefore, if a position has only finitely many black pieces and it's open for red, well, I mean, I guess it is open for it. If it has only finitely many black pieces, then the game value for red will be countable, is what I'm saying. But that doesn't prove the omega 1 of drafts, because we can imagine positions that have infinitely many pieces of each color. But it does address this flying king question. The flying king isn't going to get you uncountable game values if you only have one of them or only finitely many of them, for the same reason.
Right. So now I see, like, felt like my idea of like possible counterexample, but I mean, if you have finitely many black pieces and the first black king is the one that kind of counts down from omega 1, and so somehow activates so all the other black kings will be at the basis of some root, at the root of some other tree with countable game value, and somehow the one initial one somehow activates them and
Oh, I
makes
see.
them
Right. Yeah, maybe. Yeah.
feel, yeah, we have finitely many. But like,
I guess my argument works if there's just one, but for finitely many, I think maybe something, I don't know, one has to think about it more.
I mean, there would be finitely many kings, but they cannot be at the root of trees which have like all the countable game values, right? So yeah, probably that's
Almost certainly impossible.
yeah.
Okay.
So we need it.
Any other questions? We still have time if people have more questions.
I have a naive question.
Sure.
So we've seen the omega 1 tree many times in this presentation. Am I dumb for saying that the omega square tree is two of these, or how would you create an omega square tree?
Oh, an omega squared tree.
Yeah.
Well, think of well, we've seen a tree of value omega. Well, we can think of position with like value omega plus 1 is like just adding one extra move at the root.
Yep.
And so you can think of any position with value omega plus n, right? And then so we can just join all of them. And well, maybe this is kind of a long path, but
I think that's the best way. Yeah.
is that the best? Okay, good. I was thinking about any more. So we've constructed omega plus n. Okay, we agree. And then
Yep.
we kind of join all of these omega plus n trees into one position, like in the proof, so that the supremum of all of them would be omega plus omega. Do you want me to? Maybe I can show it again. So,
I think we have a whiteboard capability if you want to draw it.
that would be I think it's probably if you just have in mind. So we have this position. Well, maybe
Sure.
it's kind of. So we're kind of once we have all these alpha i's, we can join them and find a position which is the supremum of all of them, right? So that's kind of the key thing in this construction. So we did have a position with game value omega, and if black, we somehow force it to make well, we can kind of make sure that it has a resting place here, and so say that black is here and makes a jump here, and then it can stop. For instance, well, red pieces go down, so you could make a bend so that say that black is here and kind of actually black is here, jumps down, and then red is here, but black can stay there put so that it doesn't have to continue. Is that convincing enough that that's a position that allows black to make one extra move before reaching the root? So that's the omega plus 1 position.
Yeah.
Right? Right. So after having done that, we can actually do this for 2 free many moves. And so we can construct an omega plus n. This kind of tree. And now once we have all of them, think of here in the proof to have at the beginning of each of these branches the position of value omega. So here omega plus 1, omega plus 2, omega plus 3, and so on, omega plus n. Then the overall position will have value supremum of the successor of all of them. So the supremum of omega plus 2, omega plus 3, omega plus 4. And so that would be omega plus omega. Okay.
Mm-hmm.
Right. So that's omega times 2. So once we have that, we can just iterate this, right? And we can get omega plus 3 by doing omega plus times 2 plus 1, omega times 2 plus 2, and so on. And we redo this, take again the supremum, and get omega plus times 3. And can do this for all the finite multiples of omega. And once we have all these finite multiples of omega, we put them all here. So here we'll have, say, value omega, and then value omega times 2, omega times 3, so on. And then once we do that, the supremum of all of those ones will be omega squared, which is what you. Okay. So in this sense, we can construct all the countable game values, and yeah, that's the first kind of very interesting case of constructing, I guess.
If we're allowed to do this, is it difficult to get to omega cubed and beyond by just doing it again?
It's just the same process, just a little longer, but it's just right? I can just do omega squared plus 1, plus 2, plus 3, omega. Well, then kind of omega squared. Once you get to the omega squared times 2, yeah, that's the way that you count up the ordinals in a way.
That, I mean, to my way of thinking, it's the beauty of this tree embedding proof strategy, because the theorem, right, is that you get through all the countable ordinals by doing that. And so you can prove that you get really high game values not by exhibiting an intricate, finicky position, which is what we had to do in infinite chess until recently. But we can just get all the countable ordinals at once by showing this recursive process for how to make higher game values by assembling them from the lower game values by using this kind of branching node construction that Davide described. So I guess we're going to see the same kind of thing later, embedding the tree in positions of infinite chess as well. It's going to be a similar kind of branching node construction that we're going to see. So I'm quite excited about that. Are there any other questions?
I just wanted to quickly ask, I'm still thinking about the finite piece case in infinite drafts, and I just want to ask if the Maton N problem for finitely many pieces on an infinite draft board is clearly decidable.
Oh, I see. That's a really good question. And I have a feeling the method of my paper with Philip Schlicht and who was my other co-author? I can't remember now on that paper.
Was it Evans again? No. No, it didn't.
No, it wasn't. It
Corey
wasn't
Evans, and there's another guy who I never met except on Math Overflow.
Dan Brumvele?
I'm sorry?
Dan Brumvele, I think.
Yeah, right, exactly. I
Yes.
never met Dan, but anyways, he's also a co-author on that paper. Right, and what we did there was we proved that even in the case of chess, the Maton N question is interpretable in Pressburger arithmetic. And the key thing was that you never get extra pieces, which is also true in drafts. And the pieces that are infinitely moving move on straight lines whose equations can be expressed in Pressburger arithmetic. Because if you had a parabolic fairy piece or something, then it would break the proof. But all those things are true for drafts as well, I think. And so I conjecture that the same proof is going to work in drafts so that the Maton N or the win in N problem for a finite position should be decidable. And in fact, automatic, I think. I mean, sort of.
Okay.
It's not, I think. Because Pressburg arithmetic is quickly decidable. Right.
Excuse me, would it have to be adapted for like all these iterated jumps which are kind of zigzagging and also
Yeah, but they're still finite. If there's only finite many pieces, then it's the zigzag itself will be a bounded finite length, and there's only finitely many possible zigzags that you can do. So,
right.
So I think that proof should just work, but let's work it out. I encourage you to prove it. Yeah, that would be great if it was true. So Aaron, you had a question?
Yeah, when I was just looking at the slides, can you jump over more than what looked like maybe there's 3 in a row? Can you jump over more than 1 in a row? No, oh, that's a stopping point or something.
Wait, sorry, jumping more than?
I thought I saw it in a slide. Maybe that's like stopping the black or something. That there was like 3 in a row or something.
Yeah, it was a kind of block that you can't jump over. That's
okay.
what made it work. Yeah, the jumping had to stop at that point, like in the value 2 and 3 cases.
Okay. And can there? I'm sorry. Can there be infinitely many red pieces?
Yeah.
Yeah.
But
Okay.
2 are enough to kind of block a red piece, a black piece. So especially here in the value 2, really, red goes down and then black finds 2 of them. So it can just jump over 1 of them. So 2 are enough to block black. Yeah. Okay.
All right, then. Well, let's thank Davide again for an excellent talk. Really enjoyable.
Thank you very much.
And thank you all for coming. And I encourage you to come again. I think I'm going to give a talk I think it's 2 weeks or 3 weeks. 2 weeks, I think. Let's see. I can't look at my calendar at the moment. Can someone say, what is the date? I think it's 2 weeks from today.
Yes, it's the 5th October.
Yes. Okay.
October
So I'm
5th.
going to give a kind of introduction to a lot of different games in 2 weeks. So please come and hear that, and also invite your friends, and we'll all have a great time. So see you then. And thank you so much for coming. Bye.
Thank you.
Thank
Bye-bye.
you.
Thank you.